Okay. We're going to keep talking today about what we started on Monday, which is what I'm calling simulation-based inference. So we were looking at some slides. I'll open those back up again, and then we'll go to R and illustrate what this is talking about. Inference is where we're headed. We're going to do a lot of regression-based inference, linear regression. Generally, when we want to do statistics, we have in mind specific population parameters that we want to make statements about or decisions about at stated levels of confidence. T-tests, for example, are examples of inference. We're going to spend most of our time doing regression-based inference. Regression is a very general way to model data and to kind of extend the idea of t-tests to adjusting for covariates, non-continuous response variables with, say, logistic regression or Poisson regression. But ultimately, we will have some kind of model that says, I saw some data, and I think that such and such probabilistic relationships apply. When we do that, when we specify a model, then the inference part is about confidence intervals and hypothesis tests on parameters of that model. Could be the mean in the population, could be a slope parameter from a regression model, could be really anything. To do statistical inference, the common theme or the common requirement is that we estimate the parameter with some statistic, some number that we compute with our data, our sample data, and we need what we are calling the sampling distribution of that statistic. Because samples are obtained randomly, if I obtain a sample and compute, say, an average, sample average, and you obtain a sample from the same population, same sample size, and you create or compute a sample average, we'll see different numbers. Sample statistics are random variables, so they have distributions. We call them sampling distributions. There's different ways that we can get a sampling distribution. Teaching you right now how to do it using what's called simulation, which is arguably the most flexible of the ways that we're going to see. Maybe not the most flexible, but it's a very flexible way to do statistical inference. Okay, so we talked about this thing called the Bootstrap on Monday. And the idea of the Bootstrap is that it allows us to take, or kind of like simulate, the taking of repeated samples. A sampling distribution is the distribution of your statistic that you would see if you repeatedly sampled from the population and recomputed it. If we knew the analytical form of that sampling distribution, like suppose we could say somehow it's normal with mean 0 and standard deviation 1 maybe, then we could do inference by computing areas under that curve and getting percentiles from that curve. When we don't have an analytical expression for the sampling distribution, an alternative would be to sample from it somehow. If you don't know the actual function that describes the sampling distribution, the next best thing is to sample a bunch of draws from it. Let me show you one little example here. Let's say that, let's make some normally distributed data. I'm going to say y is r norm. So randomly r for randomly generate numbers from the normal distribution. Let's do 5,000 draws from the normal distribution with mean 0 and standard deviation 1. If I wanted, so the distribution for this population is normal 0, 1. And you can draw that, I think, let's see, there's a function called curve. Let me use this real quick. Curve that from that to that. Okay. I could draw the actual bell-shaped curve using the curve function. I'm not expecting you to do this necessarily, but I just want to illustrate what it looks like. That's the bell-shaped curve for the normal distribution with mean 0, standard deviation 1. If I know that that is the mathematical distribution, we could compute any probability we want by just getting areas under it. We could get any percentiles that we want as well. So suppose we didn't know the analytical form of that. Instead, what we did was just simulate or draw a bunch of realizations from it. So now if I, say, draw a histogram, I'm going to make it relative frequencies instead of just frequencies. There's the histogram. And let's overlay that curve. See if I can do that. Curve, -3, 3, add. Okay. The smooth curve is the mathematical reality. And if we didn't know that, as long as we could get the big sample represented by the histogram, we essentially have the same information. The histogram is representing that curve. So if I wanted a probability, like an area under that curve between two numbers, if I don't know the actual function, I can't get it exactly. But if I had the histogram, I could compute like a sample proportion. The proportion of my simulated values that are between two numbers would be an approximation of the actual probability. When we do simulation-based inference, when we do Bootstrap, we are essentially going to be doing sample with or sample multiple times, recompute your statistic each time, and use a histogram as like a proxy for the actual sampling distribution. I uploaded a new script that I want to talk through today that illustrates this. It's not exactly a biostatistics data set, but that's okay. We're just going to use it to illustrate concepts for us. So nfl.r, new script. Let's save this. Okay, so these are actually football data. They come from the National Football League in the US and the local team down in Houston, the Houston Texans. In the last season, previous season, last year, there's 16 games in a NFL season, and the Texans won 9 of them. So their record was 9 out of 16. What this script does is consider doing inference on the real probability that this team would win any given game. Consider this team as theoretically it's possible for them to play infinite numbers of games. Well, it's playing pretend sort of. On any particular game, if you put this team in front of another team, what is the probability, it's the long run average or long run proportion of games that they're going to win? That's a population parameter. We could call it P. Let me write that down over in the whiteboard. So for the NFL data, we have 16 games. And we're going to let P be the probability the Texans win any given game. Texans win a game. Because it's a probability, it means, or what a probability means is long run proportion. It does not mean, if P is 0.5, it does not mean that they're going to win exactly half of their games. If we see 10 games, we have no guarantee that it's going to be 5 wins, 5 losses. If P, the probability is 0.5, what it means is if you watch them play an infinite number of games, then the proportion is going to be 0.5. So probabilities are long-run behaviors. Probabilities are not so predictable in the short run. They become predictable in the long run. We have a parameter though, okay? So think of the population in this case. Here's a blob representing the population of all possible games for this team. And let's say we have 16 games in our data set, the season from 2015. We have 16 zeros and ones, win or loss. Suppose that's our 16 games right there. That's our sample. If we view those 16 games as a random draw from that population, which is debatable, but suppose we're willing to do that, then it's an inference problem. We have a parameter P, and in our sample, we're going to try to estimate it by putting a hat on top of the P. How can I estimate the parameter given my sample data? All right. So back in the script, let's start working through this. All right. We have 9 out of 16 games won. So my estimate of P would just be 9 over 16. That's the, it turns out, maximum likelihood estimator in this case. Our data, by the way, let me write something else here. Let's say that X is defined to be the number of wins in a 16-game season. X is number of wins. You're going to play 16 games. Imagine there's zeros and ones for each one, depending on whether you won or lost. And X is add them all up. Who knows what the distribution of X is? X has a probability distribution. It could be like normal distribution, or gamma distribution, or binomial distribution, or Poisson distribution. Anybody know what the distribution would be? Be binomial. Because we are doing independent success or fail 1-0 yes/no trials, and counting up the number of successes out of those in trials, that's the definition of binomial, a binomial random variable. Binomial would speak to like flipping a coin 20 times. Suppose the probability, it's a fair coin, so the probability of heads is 0.5. Let's consider the experiment of flipping a fair coin 20 times and adding up how many heads we got. We can model that probabilistically with a binomial distribution. In our case, we have binomial with n equal 16, and P is the unknown parameter. So again, in statistics, we have a population of interest and at least one parameter of interest. And it's that parameter that we want a confidence interval for or p-values for. Here we have a single parameter P, and we would like to estimate it. In the script, we said, let's estimate P with the proportion of wins in our sample. That is a maximum likelihood estimator, which means it's a good choice to estimate this thing. It makes sense. That's my estimate. But as we talked about last time, a statistic, which is what p hat is, it's a number computed from sample data, is random. So if we went and got another 16 games, we would not expect to necessarily see 9 out of 16 again. In fact, imagine taking many 16-game seasons and computing p hat each time. So here's one season, p hat 1. Here's another season. A bunch of seasons. And for each season, we have an estimate. If you drew a histogram of all those estimates, you have something like this. And that picture right there is what I was trying to motivate back here. It's as if we don't know the actual curve, the mathematical curve, but if we can make it as if we took multiple samples and just recompute our statistic and draw a histogram of it, it's the next best thing. So the idea is somehow we want to generate repeated draws from this population so that we can compute repeated versions of our statistic. Okay, so how do we do that? Let me do this first part real quick. I think it's a good picture to see. Before I show you Bootstrap stuff, let me say something a little bit more about statistical inference, because I want to make sure we're really clear on it. In this example, we have a team, and they either win or lose each game. An inferential question would be, given these data, 16 games, 9 wins, is that consistent or not with this team being above average? It would be above average team if its P is bigger than 0.5, say. If this team tends to win more than half its games, then we would call it an above average team. We observed 16 games and 9 wins out of them. That turns into, p hat, 9 out of 16, 0.5625. My estimate is 0.5625. But I know that's not equal to the truth because there's variability from sample to sample. So the inferential question is, okay, 0.5625, that's bigger than 0.5. Is it enough bigger than 0.5 for us to say, I don't think that this is really just different due to random chance? Is this significantly different from 0.5? So let's think about what could happen if P was 0.5. This next chunk is going to consider that. Suppose P is really equal to 0.5, so they are an average team. In the long run, they will win 50% of their games. We have a pretty small sample, just 16 observations. So even if P is equal to 0.5, you might see 9 wins just by chance. Let me just do a couple of simulations here. Suppose we're going to flip a coin 10 times. I can flip a coin 1 time by doing, let's say, R binom. Give me a randomly generated number from the binomial distribution. I want one number, and let's say 1 trial with probability 0.5. That's saying 1 time, do a single success-fail trial where the probability of success is 0.5. This is going to give me either a 0 or a 1. So that's just like I flipped a coin and I got tails. Let's flip it again. I got heads. Flip it again, heads, tails, and so on. Let's flip the coin 10 times. So 10 draws each time there's a single yes or no, success or fail. So there's 10 zeros and ones. What if we add up the zeros and ones? That will then be the number of heads out of the 10 tosses. So there was one simulation, 10 tosses of the coin, and I saw exactly 5 heads. But if we keep doing this, it varies, just by chance. Like there was an 8. It's a fair coin, and just by chance we got 8 heads out of 10 tosses. So we're trying to account for this type of variability. That's the tricky part in statistics. If the truth for this team was 0.5, then what if we did something like this and tried to explore what we might see in that scenario just by chance? So here I'm going to simulate a whole bunch of 16-game seasons. I'm going to have 1,000,000 16-game seasons. And we're going to assume, for the sake of argument, that they're really an average team. So suppose they really are an average team. Let's do n equal 1,000,000 simulations. Each time it's going to be a 16-game season, and the probability of success is 0.5 each time, we're assuming. This command will generate capital N 1,000,000 draws from the binomial distribution. Each time, the number of trials is 16, and the probability of success on any one is 0.5. So I'm going to get back 1,000,000 numbers. Here's the first 10 of them. Each one of those is a number of wins out of 16 games. So the first simulated one, there were 8 out of 16. Second was 8, and then 7, and 4. There was an 11. So you're seeing variability. The truth is 0.5. Here's a histogram. And this is a histogram showing the sampling distribution of the number of wins out of 16 games. Because we repeatedly sampled 16 games, and each time computed a statistic, which was the number of wins out of the 16 games. So treating y that we just simulated as a statistic. How many wins out of 16 games? We simulated lots of times. Here's a picture, a distribution of that statistic. So this is a sampling distribution, or it's at least an approximation of one. So what might we do with this, this information? One thing we could ask is, okay, if the truth is 0.5, how likely would it be that we would see 9 wins or even more just by chance? We're trying to kind of ask, are the Texans a better than average team? Their p-hat, 0.5625, is bigger than 0.5. So that is suggestive that they are better than average. But in terms of distinguishing that 0.5625 from 0.5, whatever the truth is, you're going to see variation around that truth. We saw 0.5625. Is that unusual? Would that be unusual if the truth was really 0.5? That's an inference question. That's a hypothesis test question. What I have highlighted on the screen is kind of like the area under the curve, which is how we talk about probabilities, areas under distributions. Area under the curve to the right of 9. What's the probability, if you're really an average team, of getting 9 or more wins out of 16, just by chance? You shouldn't win more than average because you're an average team. Just by chance, how likely would it be that you'd see a 9 or even more? That is an area under the curve for the sampling distribution. We can approximate it as a proportion. what proportion of my 1 million simulated seasons had 9 or more wins. And this number, whatever that number is, that probability has a special name. That's the p-value. P-value. P-value is the probability that if the what we'll call the null claim or null hypothesis is true, in this case, p equal 0.5, their average. If that's true, what is the probability that you'd see data like yours or data that's even more indicative of the null not being true? So like yours or even more extreme. In our case, since we're considering are you above average, as or more extreme is 9 or bigger. If p is 0.5, what's the probability that you'd see a 9 or bigger just by chance? That's called a p-value. And what we're going to do with the p-value is ask, is it small? If the p-value is really small, then that's saying it would be very unlikely to see what you saw if your hypothesized value were true. If that's the case, then that hypothesized value, the null hypothesis, is probably not right because it's not consistent with the data. You wouldn't see data like you saw if that were true. So it's an inductive way of reasoning in the sense that we're asking, given my data, what can I say about probability models and parameter values that are consistent with my data? All right. So in our case, in this case right here, we have a lot of red on this picture. In fact, if I were to compute the proportion, let me write this differently first. If we were to add up how many of those 1 million simulations were bigger than or equal to 9 and divide by how many simulations I did, that's the same thing as computing the mean of y, the mean of y greater than or equal to 9. Y greater than or equal to 9 is going to give me a bunch of trues and falses. If you try to do arithmetic with trues and falses in R, it will treat trues like 1s and falses like 0s. So when I sum up those trues and falses, I'm going to get the number of times that it was 9 or bigger. Either one of these will give me the same answer. And what we then have is that my simulation-based probability or p-value probability is 0.4. If they were an average team, the probability you'd see 9 or more wins out of 16 games just by chance is 0.4. And that's not a small number. That's usually we will say, I'm going to reject that claim, that null claim, if the p-value is small, and common choices for the threshold determining small are 0.05 and 0.01. If your p-value is smaller than, say, 0.05, then it's standard practice to say that's strong enough evidence to conclude that that null hypothesis is not the right one. In this case, because the p-value is substantial, what we have is insufficient evidence to conclude that they're a better than average team. We would fail to reject the null hypothesis in this case. So let me come over here and write down hypothesis language. We are considering what we'll call a null hypothesis that the population parameter is 0.5. And we're considering an alternative hypothesis that they are better than average. When we do hypothesis testing, we're trying to make a decision based on the data. To make a decision, we formulate things into two competing hypotheses. The null hypothesis is what you believe prior to seeing evidence to the contrary. It's the boring status quo, nothing to see here hypothesis. The other one, the research or alternative hypothesis, is the one that you are interested in actually testing. You suspect, maybe, that that's the case. You're collecting data in order to check whether that's the case. And let me just write down, p-value is the probability if or when the null hypothesis is true, when H0 is true, of seeing a statistic value as or more extreme. As the value we observed. So we observed, in this case, a value, a statistic value of 9 out of 16. How likely would it be to see 9 or more if the null is true? And what we just figured out is that the p-value is about 0.4. We typically would reject the null hypothesis if the p-value is less than, say, 0.05. Sometimes we change that, but that's the most common choice. Because my p-value is not less than 0.05, we fail to reject. In this case, with p-value bigger than 0.05, we fail to reject H0, the null. We didn't prove that the null is true. All we did was say we can't tell that it's not true. Just like if somebody goes to court and they've been accused of a crime, you are assumed innocent until somebody can prove beyond reasonable doubt to the contrary. And if you're not convicted, you get to go home. That does not necessarily mean everybody thinks you're innocent. What it can mean is that we just didn't have enough evidence to prove your guilt. Hypothesis testing operates similarly. Okay. So I haven't shown you the bootstrap yet. We didn't need the bootstrap up here because we know the distribution of our data in this example. We're doing binomial stuff, 16 success-fail trials. So the distributions that we need are binomial distributions, which we can just access directly. So what we're going to do now is pretend that we didn't know that. What would we do if we didn't have the capability to directly sample from this distribution? This is where the bootstrap comes in. And what I'm going to illustrate with the bootstrap initially, I will show how to compute that p-value. The two kinds of inference that we're going to focus on in this class, confidence intervals and hypothesis tests. We just computed a p-value for a hypothesis test. But I'm going to show you how to do the same thing with Bootstrap. Before I do that, I'm going to show you how to use the Bootstrap to get confidence intervals. Typically, you would like to have confidence intervals and p-values. A confidence interval gives you a range of values about which you have a stated level of confidence for capturing the population value. Whereas the p-value quantifies like strength of evidence with respect to a specific claim. So I think an ideal way to present your statistical results is to say, I did an experiment, I tested this hypothesis, I got a p-value of such and such. And my estimate of the parameter value of interest is, here's a confidence interval. So So both of them, I think, should be used. Okay, so Bootstrap, let's see. Back in the notes, where did that go? Here's the idea of the Bootstrap. It is an iterative algorithm. It's a big for loop, basically. And what we do is, for many times, call it capital B, we take our sample. In our case, we have 16 zeros and ones. That's our sample. That's our data. Take your 16 zeros and ones and sample with replacement from them. In our case, our observed data are the zeros and ones. So it's like, let's say x1, x2, ... x16. These are zeros and ones. So suppose we have, like in the script, I wrote down the actual record. They lost their first game, lost their second game, then they won one, lost, lost, win, lost, and so on. My data. So to sample with replacement, what does that mean? Let me go back to R for a second. Here's a little toy vector. Let's do 1 to 10. X is the numbers 1 to 10. If I use the sample function, I can say sample from X and do not sample with replacement. So there's an argument called replace, which is for yes or no, should we replace? If I sample without replacement, all it does is shuffle the numbers 1 to 10. Every number's in there exactly once. But if I sample without replacement, with replacement, then you can have multiple entries of the same thing, and you can have one or more of the original numbers not represented at all. For example, 6 is not in here. When we've done this sample with replacement, this is, it turns out, a bona fide sample from the population, or it can be treated that way. Even though we only have one sample from the population, it turns out that if you sample with replacement from it, it's as if you just took repeated samples from the population. So just like we did with the binomial simulation up here, we simulated lots of samples like ours, and for each one of them we asked, was the win count bigger than or equal to 9? Here's how I can do that without knowing the actual distribution that applies. So we're going to create Texans 2015 as our observed data. And let's increase this some. I'm going to make, instead of 250 bootstraps, let's do 1,000. And the essence of the bootstrap is inside the loop. So if you want to repeat something capital B times, you want to run an operation capital B times, you can put it inside a loop. Check out our cookbook for loops. To take a bootstrap sample from these data, I sample with replacement. Sample with replacement from all those zeros and ones, add up the number of ones, and divide by 16, which gives us a proportion estimate, a p-hat. This loop is going to compute 1,000 p-hats. Our observed p-hat was 9 out of 16. Now we're going to have 1,000 p-hats that are just like ours. Bona fide estimates, as if we took a new sample from the population. So let's run this, and I'm going to make a histogram of the resulting 1,000 p-hats. P-boot. 1,000 numbers. Here's the first 10 of them. Those are all sample proportions out of 16 games that are comparable. It is as if they are samples from the same population that we got our data from. Here's the histogram. It's a little bit coarse, like there's no counts in between that, in that bin right there, or in that bin, or in that bin. That kind of coarseness comes because of the relatively small sample size. And then suppose we did this. We have a 1,000 p-hats, which represent to us the sampling distribution of p-hat. The sampling distributions are the key to doing inference. And in particular, if I take, say, the 2.5th and 97.5th percentiles of my Bootstrap sampling distribution. Suppose I come over here. Let me draw it on the whiteboard. Let's say after the Bootstrap, after B, Bootstrap samples, we have a p-hat 1, a p-hat 2, and remember p-hat, let's call it p-hat 0, I guess. The original one that we saw was 9 out of 16. We'll call that the observed statistic value. So here's a histogram of all of our Bootstrap p-hats. And what I'm saying in the script in just a second here is, if you come over to this side and get the 2.5th percentile, and then go over to this side and get the 97.5th percentile, let's call it A up to B. The interval from A to B is what's called a 95% confidence interval for the parameter P. Which is inference, statistical inference. A confidence interval is inference. I'm this confident about where the truth is. And while it probably doesn't look magic yet, what's magic about this is we got this without saying anything. We didn't have to say anything about what the distribution of the data was. All we did was take data, 16 zeros and ones, and that's it. We used this generic technique of resampling to make it as though we know the sampling distribution of our statistic. And using that histogram, we can step right into confidence intervals. P-values also, although there's a little bit of a twist to get the p-values. So let me show you this simulation that illustrates why or how this works. Okay, so let's play pretend and say that P, the truth, is 0.5625. We're going to simulate under this scenario. Let's say we're going to play 16 games, and the true value of P is 0.5625. We're going to do 1,000 simulations. These are not bootstraps. These are full simulations. Each time I do a simulation, I'm going to make it as though we have the data that we started with the Texans. 16 zeros and ones, that's it. So inside this loop, over capital M simulations, we're going to start by getting a sample season. We can compute our observed statistic, p hat, for that sample. And then to do inference, to get a confidence interval, we can do the bootstrap. So inside that first loop, over 1,000 iterations, simulate a sample, then do the bootstrap, and then use the bootstrap to get percentiles. That quantile function gives you percentiles. And what I'm doing is, I've written this generally, QQ up above, and desired confidence allow me to, by just changing desired confidence, go between, say, a 95% confidence interval to an 80% to a 99%. So I'm going to encourage you to vary this value right here and see what happens when you rerun this many times. Let me run it one time. Might take a moment to run because we're doing 1,000 iterations, and inside that we're doing 1,000 more. Okay, so it's done, and let's see what we have. There is this matrix CI underscore capital M, which is 1,000 by 2. There's one row for every simulation that we just did. And there's 2 columns to hold left and right endpoints of a 95% confidence interval. There's the first 6. So the very first simulated data set that we got, when we did the bootstrap, we ended up with a 95% confidence interval from 0.3125 to 0.8125. And I have 1,000 of them. This is the picture that you saw in the slides that I pointed to as interpreting your confidence intervals. We just did 1,000 confidence intervals, all under the scenario that P is 9 out of 16. Every single one of those horizontal line segments corresponds to one of those simulations where we had 16 zeros and ones. We did the bootstrap and got 2.5th and 97.5th percentiles of the resulting distributions. So the topmost horizontal line segment is green because it overlaps with 9 out of 16. The truth in this case, the true parameter value was 9 out of 16. We set it that way by doing a simulation. And 95% of our 95% confidence intervals can be expected to contain the truth. The red ones are the unlucky 5%. There was nothing wrong with the way we collected the data for any one of these red ones. The data were collected just fine. It was just by chance you got misleading results. So again, try varying the confidence level. Like if I changed this to 0.8, then I would expect 80% of my intervals to contain the truth and 20% to not. Change it to 99 and you change it accordingly. Okay, we're out of time. Next time we'll go through what follows, which is how did you do a hypothesis test with Bootstrap. Once we know the Bootstrap, we can apply it in a very wide range of applications. Correlated data, survival analysis data, regression, logistic regression, pretty much anything. If you can just sample with replacement, you can do inference. Okay. Any questions before we end? Homework 2 is coming. I think tomorrow. I'll post it tomorrow. Okay? See you Friday.